for group number 5. These are my colleagues, Medina, Sosa, and I'm Mike Horta. Today we're going to be talking about a senior design project, Ocean Hydropower Power Station. To give you a brief outline of this presentation, we first want to talk about problems and issues the world faces and the lack of energy. We also want to give you motivations and goals for this project. And we also want to give a brief history of what's been explored and what's yet to be explored. Also talk a little bit about different alternative designs and a final conceptual design for this project.
We decided to take on this project because of the rising need to find new renewable sources of energy that can counteract for the increasing population and increasing energy consumption. This chart from the U.S. Information Administration shows the total worldwide energy consumption from the years 2008 to 2012. As you can see, the total energy consumption is steadily going up. These readings are given in quadrillion British thermal units. And since here in the U.S. we use English units to convert it into gigawatts, it would be about 155 gigawatts just for 2012 alone. Population also plays a huge factor on energy consumption. It is estimated that in the next 50 years, there will be an additional 2 billion new individuals living among us. If each one of these individuals uses just one 50-watt light bulb, that would add up to a total of 100 gigawatts of energy that needs to be accounted for, on top of the energy consumed by the people already living here. Finding a cheaper source of energy is also another reason why we took up this project. This chart gives the levelized electricity cost, LEC for short, of different sources of energy. LEC is the total cost of building and operating a power plant divided by the total amount of power that power plant will produce over the course of its lifetime. As you can see from the chart, hydropower is not the initial cheapest, but it is one of the best alternatives, and with the right amount of investment, it could show promising results.
There exist government cost incentives for usage in renewable energies in both the public and private sector. Since 2009, there has been a 53% increase in the usage of these technologies, thus reducing the use of fossil fuels significantly. Our simple design will result in low maintenance costs, and of course, our power input is virtually free because it's used from the sustainable power created by the earth. To understand where we want to take this idea in the future, we need to get a better understanding of the past. In 1799, a Frenchman named Girard was responsible for the first wave patent power. However, his idea wasn't very popular, and it wasn't resurrected again until the 1940s by a Japanese man named Yoshio Masuda, which researched many different types of wave harvesting devices around the world, which now are still being used off the coast of Brazil. In 1973, when the oil crisis hit and gas prices skyrocketed, the government poured funds into renewable energies such as wave harvesting. In 1997, Ocean Power Tech was founded, one of the largest in the United States, which was later bought by an Australian company. And in 1998, Palamas Wave Power was founded in Scotland. And in 2009, the Clean Energy Tax Stimulus Act was brought about by Obama, with a large increase in its funds being poured into renewable energies. This figure here demonstrates the difference in heights around the world, the difference in wave heights around the world, with the red being one of the largest and the blue being the smallest. So we're going to be using the difference in wave power as our source of power input. This power, by time, is going to give us our viable energy, which presents our challenge, to create a device that efficiently transforms this wave energy into electrical energy. Our team came up with different alternative designs to produce our final conceptual design. Our first alternative design was inspired by the Beta Stirling engine. The piston shown here would be housed in a buoy on top of the water, and the gears and cranks would be housed in a floating structure also, but underwater. As the waves would come, the buoy would move up and down, turning the cranks, producing the motion and potential energy.
For our second alternative design, we had a lever spring mechanism. This system would be transforming linear motion to rotational motion. How this system will work is you have a gearbox at one end, followed by a lever, followed by a cable, and a weight at the end. The system will be in equilibrium, having any force or any wave approaching and making the lever to begin to oscillate, creating a rotational motion, followed by the gearbox and followed by an alternator creating electricity.
This design alternative focuses more on the structure of our design. This structure will consist of two hexagonal shaped pipe structures that will enclose all the electric components of our device. The structure itself will be covered in a plastic membrane that can be formed into any shape, giving our design an aesthetic element. It is our hope that through the use of this plastic membrane, we can make our design resemble some type of aquatic life form, such as a jellyfish floating in the water. We would also like to incorporate LEDs and fluorescent colors to help improve the visibility of our device during the nighttime and under harsh weather for local boaters.
After taking into consideration all of our alternative designs, we came up with a final conceptual design. As you can see, we have three main components. We're going to have a retractable cable, followed by a torsional spring. Having these two components mounted on our structure, the structure will be floating over seawater. And this retractable cable, we'll have it anchored to the seafloor, so when any approaching wave hits the system, it will create a linear motion and create a rotational motion. At the end of these two components, we're going to have a set of gearboxes, aiming for a 25-to-1 ratio. And once the system begins to oscillate, we'll be able to create a rotation to be able to power our alternator to produce electricity.
The plan of action for our design is to make our device as simple and efficient as possible. We plan to produce a rapid prototype within the next few months so that we can start conducting testing in both controlled and uncontrolled environments, as well as running full structural analysis using SolidWorks.
For our global integration, we knew one of the problems was the lack of energy worldwide. So one of our main points was to be able to create a system that was efficient, to be able to help the cause of the lack of energy. Also, we wanted to aid in the development of renewable energy since there's so much to be explored in that field. Also, we wanted to create a versatile installation to be able to have this system to be able to implement the system all around the world, since there's different types of wave patterns all around the globe.
This is the breakdown of our project. It consists of researching conceptual design, SolidWorks calculations, testing our prototype, our thesis paper, and our final design. Like I mentioned earlier, we would like to have a rapid prototype within the next few months, and we hope to be wrapping up our project by mid-November.
Our team is prepared to use the sustainable, renewable energy to produce this energy. This field is one of the least pioneered in renewable energies, and of course, this is one of the most sustainable. Our team is prepared to create a simple design, giving an economic feasibility, producing economic feasible features, and remaining in low maintenance. And of course, upon success, we'll be implementing this design globally. Does anybody have any questions?
Let me start off. You mentioned that your device will be anchored to the seafloor.
Correct.
To what extent have you accounted for submerged vehicles and the safety of your system and of those submerged vehicles?
Well, that's why we want to, like I said, put it in a plastic membrane to protect not only our device but also local sea life. We do have to do more research on, local boating regulations and underwater
Fish population, things like that. It also depends where it could be, where it would be placed. So different regions have different standards.
And also for one of our other alternative designs, that was one of our main designs, to have it anchored to the seafloor. But we could also have it floating with a weight on it, because what we do need is a force to be able to create the oscillation on it. So it wouldn't have to be anchored to the seafloor.
So there's some safety issues that you're going to have a real good look at and make some provisions.
Right.
Yes.
Okay, could you present to me again your summary of the global initiatives and considerations? So how did that deal with the established components of global initiatives, which is awareness, perspective, engagement?
So awareness, we are aware that the need of energy is out there. I think all of us come from different types of countries. Where I can personally say where I come from, there's power outages all over the country all the time that can run from 1 to 6 hours sometimes. So the need is out there. And so we're thinking about places like that Now, places like Japan, where there's maybe not so many power outages, but energy is extremely costly. So if we're producing this technology, and we can reduce the cost of energy significantly.
Well, I would suggest that you emphasize those components, because us here as evaluators, that's the matrix line items that we have to evaluate you, and it wasn't very well addressed. Does that make sense?
Yeah, one question. On that chart, you have hydroelectric power being 65%. That includes dams and all that, right?
Dams and rivers.
One question I have about implementing this thing is, I'm not sure if you touched on it, but the reason I'm asking is I don't know. My understanding is usually you need 3,600 RPM, time for 60 hertz of power and all that. So it looks like the RPMs here are going to be erratic. It's going to be also very low. So how do you produce electricity to run a 60 hertz device?
So the buoyancy, we need a hard force, because we're trying to implement a gearbox, which is going to be a 25-to-1 ratio for that reason. But then for a ratio so big, you're going to need a hard force. So say if we do have it anchored to the seafloor and with a strong buoyancy, we could be able to multiply the small RPMs that we have to be able to output a higher RPM rotation speed to the alternator.
All right, so that's independent of your start-off frequency?
No, it's not. It's determined also by the difference in height. So the greater the height in the wave, the greater the power in the RPMs, the torque.
Could you tell me about the engineering standards that you?
Yeah, so the engineering standards for this typical device, which is like a buoyant, similar to a buoy, wave energy, they're right now being in research transition. So there are standards, however, they're not set standards. They're trying to implement international standards for this, and it's not per region, whereas different turbines are per region, engineering standards, are per region. Different types of wave power devices are per region these standards. However, for this specific technology, they're trying to implement international standards which aren't set yet, which is why I didn't implement them in the presentation.
I guess I have one final question. What was the division of labor for this team? Describe what each member did and what each member expected to do.
Well, I focus on doing research on the worldwide need, energy consumption, population increase, the cost analysis of our device.
Yeah, I focus
Do you have
more-
a slide on that?
We broke it down into the team separation, but not individual separation. Just because we don't want to only focus on like, oh, Carlos will be the manufacturing engineer, I'll be the analysis engineer, and Mike will be the economic engineer. We kind of made it so that, yeah, we are focused on different parts of the project, but all are kind of integrated somewhat.
Or is there equity?
Right.
Is there equity in the division of labor?
Oh, yeah.
Thank you, guys.
Thank you.